Well, hello again. In this example, you will learn how to compute seismic design loads for a building according to ASCE 7. We're going to look specifically at this 4-story building. We're told a couple of pieces of information about it. First off, that it's an intermediate concrete moment frame. We're also being told that it is a hospital and that it is located in Cincinnati, Ohio, which has this particular latitude and longitude. And finally, we are told that the soil type on which it is being built is what is called a soil type B, which is a fairly stiff soil. So we will go through the process here to compute what the story forces are. That is these F2, 3, 4, and the force that should be applied to the roof. That would be equivalent seismic loads. Step number 1 for this is we need to identify the fundamental period of the building. This is essentially the amount of time the building takes to complete one oscillation. So we're talking about vibration here. In ASCE 7, we are given an approximate calculation, so that's what the A stands for. Approximate calculation for the period is we take this factor C sub t, multiply it by the total height of the building, and that is raised to some kind of a power x. We are told that for a concrete moment frame, these are the factors that we should be using, so let's go ahead and plug those in. TA is equal to 0.016. We now need the total height of the building, so let's go back here, make sure that we understand that. Total height then is of course right here, so H sub n is 48 feet, and we are asked to actually put that in units of feet, so this is 48, and that'll be raised to the power of 0.9. This will compute out to be 0.521, and the units on that will be seconds. Once again, I want to remind you that the A, that subscript A, says that it is an approximation of what that fundamental period is. Step number 2, we need to identify the design accelerations. That is SDS and SD1. To do this, we are going to use a design tool provided to us by the USGS, and we go to this particular website. We can plug in our site coordinates and then also identify the soil type that we are dealing with. What I want you to do is I want you to notice that this tool will then provide for us what those design accelerations are. So 0.096 g and 0.052 g for those two design accelerations respectively. Step number 3 is we need the response modification factor R, and the problem statement actually gave it to us here. For an intermediate concrete moment frame, R will be taken as 5.0. Next thing is identify the importance factor, and this is based upon the use of the building. And so we've already identified this is going to be used for a hospital. So we notice right down here that if we have a hospital, that is a risk category 4. And when we have a risk category 4, the factor should be this importance factor, I sub E, should be taken as 1.5. Moving right along, next thing is we need effective seismic weight, which is we denote with this capital letter W. All we have to do there is sum up the total amount of weight. So we'll say W is equal to 400 kips plus 500 kips plus 400 kips plus 150 kips. And so just to confirm that, it is the total weight of the building is what we are looking at. And that will total out to be 1,450 kips. The next step is going to be to compute the seismic base shear. And just to be clear on this, the base shear is the amount of force that develops at the base of the building. And we denote that with the capital letter V. ASCE 7 gives us a couple of equations we need to check. So the first one is base shear is computed as SD1 divided by TA divided by R, and that quantity is divided by I sub E, and this entire quantity is multiplied by W. So let's go ahead and get that. Our SD1 value is 0.052, 0.5215. Here's our R factor and our importance factor. We will multiply that by 1450 kips, and this will compute out to be 43.4 kips. However, ASCE 7 says that our base shear will not have to be greater than this. SDS divided by R, and that quantity is divided by IE, multiplied by our total weight, which is that W. So let's check this one out. 0.096. I'll divide by 5, divided by 1.5, multiplied by 1450 kips, and this will work out to be 41.8 kips. Now that's a not greater than, but there's also a minimum that we need to check. So ASCE 7 says that V min is equal to 0.044 multiplied by SDS, so this is the 0.096 multiplied by your importance factor multiplied by W, so 1450 kips, and this will work out to be 9.2. Okay, so your base shear has to be at least 9.2, but doesn't have to be greater than 41.8. So we will go ahead and use this. Note here, this is 41.8 kips. Okay, so the real challenge now comes in taking that base shear and distributing it to the various floors. We are given this equation right here, so this is the story force. Here's our base shear, and then we've got this factor, which at first glance can seem very confusing. But if you just start breaking this down to the individual pieces, it isn't too bad to be able to handle it. So the first thing I want to do is I want to calculate this factor K, and it is based on the period. So we use that T sub A that we computed before. So here's K. So we get 1 plus 0.521 minus 0.5, all divided by 2. That computes out to be 1.01. Now that's pretty darn close to 1, and we may be tempted to just go ahead and use the value of 1 for that. However, to be completely proper here, we will go ahead and carry the calculations out as we are told to do. And so the next thing I'm going to do is let's go ahead and compute this value in the denominator. So that says we need to sum where I is equal from 1 to n. In this case, we have 4 stories. So let's go ahead and put that in there. We have Wi, Hi, and the Hi is raised to that power of the case. So Hi is the story height, Wi is the weight at each level. So right here, you've got that W4. Here, you've got the W3, and so forth. So let's go ahead and get that value here. So we'll take here 12 feet raised to the 1.01. And let's get a clarification. H represents the total height for that particular level. So for story 2, that would be the height. For story 3, it would be this. Story 4 would be this. For the roof, it would be this. Plus here, 500 kips and 24 feet. Plus 400 kips times 36 feet plus 150 kips times 48 feet. Notice all those are raised to a power. And so this will compute out to be 39718. And it works out to be the units of kip feet. Okay, so that was the denominator. And now what we want to do is go ahead and compute what the story forces are. And so that would then involve us also getting this numerator value for each of the individual cases. So the force at 2, take 400 kips, 12 feet raised to the power of 1.01, divided by that denominator, 39718, and then go ahead and multiply that by our base shear. That will work out to be 5.2 kips. Let's go ahead and get for story 3. 500 kips, 24 feet. Divided by that 39718. And this is going to need to be multiplied, every one of these, by the base shear. That will come out to be 13.0 kips. Moving right along, let's get for story 4. 400 kips, 36 feet, raised to the 1.01 with that denominator. And that gives us 15.7 kips. And then finally, for the roof, divided by the usual denominator, multiplied by base shear, gives us 7.9 kips. So those are the story forces, and we can go ahead and even write those on here if we would like. So this is 7.9, this is 15.7, 13.0, and 5.2 kips. And that had better equal the total base shear, which is 41.8 kips. I'm going to just come back here just as a confirmation for you. F2 plus F3 plus F4 plus F roof should equal 41.8 kips. If the sum total of your story forces do not add up to your base shear, you have done something wrong. Go back and check your mathematics. Well, that concludes this example, and as always, it's a beautiful day for studying structures.